Recharge Zone Podcasts. I'm your host, Brent Doty, joined with my co-host, Ann Margaret. Hi, Ann Margaret.
Hi.
And we have a special guest today, Senior Modeler Logan Schmidt. Welcome, Logan.
Thanks for having me.
Thanks for being here. So Logan is a modeler extraordinaire, but today we're talking to him about some other research interests he has, and that's his research in the Vadose zone, which is the name of our segment today. Another name for the Vadose zone is the unsaturated zone, and Logan's going to be going all into this, so don't worry. We're going to talk about his research interests, why the Vadose unsaturated zone is important, and all about that. So let's get going. So, Logan, can you explain a little bit about this unsaturated zone? What is it, where is it, and why should we care?
So the unsaturated zone is all of the material of the earth between the surface and the groundwater table. To back up even a little bit, in case people haven't thought about this, which sometimes they haven't, is that anywhere on earth, anywhere like on terrestrial earth, if you dig deep enough, you'll hit water. There's a water table somewhere everywhere in the earth. Sometimes it's deeper, sometimes it's more shallow, depending on where you are. But there's always water. There's always a zone of saturation somewhere in general. And everything above that water table is considered the unsaturated zone. And it's an important part of the hydrologic system. But it has you have to use different sort of physics to describe the hydrology of the unsaturated zone compared to the saturated zone, which is everything beneath the water table.
I like breaking it down like that.
Yeah. And so when you say saturated versus unsaturated zone, the saturated zone is essentially the aquifer, and then the unsaturated zone, even though we're saying unsaturated, that just means it doesn't have as much water as the saturated zone, right? There's still water in that zone, in the Vadose zone.
Yes, there is, in general, water in the unsaturated zone. And in general, you could consider it to be less accessible than water in the saturated zone. If you drilled a well into the saturated zone, water would spontaneously flow from the saturated zone into the well, and you could pump it out pretty easily. That won't happen in the unsaturated zone. A technical definition or distinction between the saturated and unsaturated zone is that in the saturated zone, the water is under positive pressure, and everything in nature moves down an energy gradient. That's true for the unsaturated and the saturated zone. The energy gradient for the saturated zone is almost always most strongly dictated by gravity, and so that's just water running downhill. In the unsaturated zone, the gradients are a little different, and the forces tend to make the water stick to the solid phase of the unsaturated zone, and so it won't flow out of it's more tightly bound. The water in the unsaturated zone is bound to I'm saying the solid phase. I haven't explained that. So another distinction between the unsaturated zone and the saturated zone is that you can consider the saturated zone a sort of two-phase system. The phases being the solid phase, which is the rock or sand, potentially, whatever earth material is comprising the wherever the part of the earth you're in. The unsaturated zone is a three-phase system where it has the solid phase, the liquid phase, and a gas phase. Gas in most unsaturated zones, those phases would be, again, the solid phase would be whatever minerals, rocks, or soil you're considering in that part of the world. The liquid phase is some water with whatever's dissolved in it. And then the gas phase would be typically something like atmospheric air.
Oh, interesting. And so I know you kind of described this before, but you said the unsaturated zone is kind of like a sponge.
Yes.
Okay.
Another sort of big picture thing I probably should have talked about off the top is that, the earth is like a sponge in that all earth materials are porous. Porous is an interesting word, but you can think about the pores in a sponge are the little holes in the sponge. All earth materials have little holes like that, and they permit fluids to enter and exit them. And so really when you're any study of groundwater, whether you're thinking about the saturated zone or unsaturated zone, is a study of flow through porous media. The media being the earth materials, and the flows being either the liquid or gas that you're interested in. And like a sponge, the earth can hold water and transmit water.
Interesting.
One way I like to look at it, this is the recharge zone podcast. Everyone knows what the recharge zone is. That's where the water infiltrates and goes down to the aquifer. Well, where is it infiltrating through? The
Yes.
unsaturated zone.
Okay.
The aquifer is not at the surface. The water table is not right at the surface. It has to move through some media, some rock to get down there,
Mm-hmm.
and it's moving through that unsaturated zone.
Interesting. Okay, so the unsaturated zone, is it located within all of the zones of the system, like the
Zone.
contributing zone, recharge zone, artesian zone? Is it there, or is it just in the recharge?
It's everywhere. Everywhere that there's land, there's going to be, unless you have water, unless the water table is at the surface, which it is in some places like a wetland or something like that, there is an unsaturated zone.
Mm-hmm.
And it's important. Also, this is another thing to keep in mind, is that the soil is a very important part of the unsaturated zone. Most of people that study the unsaturated zone are studying soils, and soils are obviously extremely important for a lot of global systems. All of terrestrial vegetation relies on the water and biogeochemical processes that happen in soils.
Mm-hmm.
A lot of the energy that comes from the sun that hits land on Earth goes to evaporating water that's stored in soils. Soils are a big part of the energy budget. Soils are a big deal for a lot of reasons. Basically, all of civilization relies on services that are provided by the soil. And the soil is an important part of the Vadose zone, because the soils, like a sponge that isn't dripping wet, are not always full of water. They're unsaturated. They're part of the unsaturated zone. But in the Edwards Aquifer region, soils are only a small part of the entire unsaturated zone. The water tables can be hundreds of feet deep in a lot of places, and the soils are only a few centimeters thick in most places. So the rest of the unsaturated zone, you have to imagine what is the rest of the unsaturated zone in this part of the world. And anyone that's drilled a well knows that it's mostly rocks. And so that's a less well-studied part of the unsaturated zone, is how is water stored and transmitted through unsaturated rocks.
Mm-hmm. And is it different type of geologic formations, or is it like loose rocks? Like, would that be, like, what is it?
In the Edwards Aquifer region, it's different everywhere in the world, but in the Edwards Aquifer region, it's a lot of weathered and fractured carbonate rocks. But it's very complicated, and there's definitely, with hundreds of feet of depth, you can have many different sorts of, there's lots of stratigraphy, lots of different geologic formations between the surface and the water table.
And that's so interesting, because it's something that you can't see. So that's what you all do. You all study that. Because I'm like, is there a simple answer? Is there one thing? Is there 5 things? But no, it's not a simple answer.
Well, I'm glad you mentioned that, because at the Field Research Park, studying the unsaturated zone is a huge part of the research going on out there. So we're looking at how can land management potentially benefit diffuse recharge, which is that recharge that occurs between these basins, between rivers. So that recharge that occurs just in the area between those discrete or direct recharge features.
Yeah, we were talking about the Edwards Aquifer System a little bit, and the Edwards Aquifer is a special kind of aquifer in that it's a carbonate system, which means that because carbonate rocks, limestones, dolomites, are soluble, rainwater is acidic enough to dissolve those rocks, and over geologic timescales, you get features called solutionally enhanced, like conduits, and solutionally enhanced features that create large pores at scales that a person could fit in. So that would be like a cave. And those really determine a lot of the properties of the Edwards Aquifer, because we have solutionally enhanced features that allow surface water, like in streams and rivers, to directly recharge the aquifer. So the Edwards Aquifer is special because it recharges very quickly. If you have a big rainstorm in the right spot, a lot of water can go into the aquifer, and that water can stay there it can sustain the spring flows and the pumping of the aquifer for a long time. Other kinds of aquifers, like that are situated in unconsolidated sediments, maybe like in the Central Valley of California, for example, they don't recharge quickly because water has to travel through the Vadose zone to get to the aquifer, or maybe the aquifer is completely confined and there's no connection to the surface and doesn't recharge at all. So that's one of the things that makes the Edwards Aquifer special, is that it recharges quickly because there are these shortcuts that bypass the unsaturated zone. But the unsaturated zone plays an important part in the hydrology and availability of the water in the Edwards Aquifer, but in a less direct way than in other aquifers. And we can talk about how that manifests.
Yeah. Okay. So now that you're saying that, so essentially it is soil and other types of formations that make up the Vadose zone or the unsaturated zone. And what happens if, and I know you're all are studying this at the FRP, but what happens if within the Vadose zone, like the soil is not in good health or those types of things? Is that also something that y'all are studying to see the infiltration of water within that?
The soil is a great sponge, if you will, and it helps. That's what we're studying at the FRP. Can enhancing the soil enhance this infiltration process by letting that water go slowly over time versus all quickly, or there's too much runoff kind of thing. And that's what I want to get into, Logan, is I think you've explained very well what the unsaturated zone is and why it's important, but what methods do we use to study it? Obviously, we can't see it. It's below us. So talk about the concept of geophysics and how that applies to your research.
Yeah, so making measurements of the unsaturated zone is, there are textbooks just about that because it's pretty difficult. The methods you would use and especially in the Edwards Aquifer region, where we talked about, we have a very thick unsaturated zone, hundreds of feet thick, made out of very complicated materials. Soil is complicated. Any thimbleful of soil is full of all sorts of different microbes, pore structures, animals, fungi, roots, and so soil by itself is very hard to quantify and characterize. And soil is much more well studied than the weathered and fractured bedrock beneath the soil. So we're dealing with both in the Edwards Aquifer region. So it's a very complicated system, and much of it is understudied. And the reason why is that it's hard to study the deep Vadose zone. Groundwater systems, the conventional methods you use to study the saturated zone don't work in the unsaturated zone, like we talked about. You can't just put a well into the unsaturated zone and monitor how water levels change, because there will be no water level in that well.
Oh yeah.
And then conventional methods you would use to study the soil don't work when you're talking about bedrock, especially when it's very deep. So you can't, for example, like take a little shovel and get a scoop of bedrock and bring it to the lab and make measurements of it, because the bedrock is cemented and it's not unconsolidated like a soil. So there's less of a history of studying the deep Vadose zone, especially in bedrock, and there are less methods available to us to study it. One set of methods that does work for measuring the unsaturated zone, like Brent mentioned, is geophysical methods. There are lots of different kinds of geophysical methods. Geophysical methods were originally, in most cases, deployed to understand economic geology, like mining or exploration for hydrocarbons, oil and gas. But those methods work for understanding the unsaturated zone as well. And at the EAA, at the EAA's Field Research Park, we're employing two sort of cutting edge or sort of advanced, sophisticated methods to study an unsaturated zone. One is called nuclear magnetic resonance, which it's an electromagnetic method that uses the same principles as medical MRIs. And another is electrical resistivity, which is a method that is another electromagnetic method that tells us information about the unsaturated zone. We're using other methods, conventional soil. At the FRP, we're also using wells to understand the groundwater system, and we're using soil methods like soil moisture meters and water potential meters as well, so we can get a full picture from the surface. And we also are measuring evapotranspiration directly and evaporation. So we've got a suite of methods to understand the entire Earth system from the low atmosphere all the way to the groundwater system at the FRP, and including the deep unsaturated zone, which is less common.
And so I remember seeing pictures a few years ago of you all, or maybe it was a year ago, but when you all did the borehole drilling thing, and then so in that, when you do that, are you getting some of the unsaturated zone and then the saturated zone in there, and then studying that in those, I don't know those boxes that you all put them in?
Yeah. To drill a hole or to drill a well that reaches the groundwater, you have to drill through the unsaturated zone. Unfortunately, for well owners, because that's a lot of money to drill all the way through the unsaturated zone. But at the FRP, we have something that now is relevant to mention is that in all of hydrogeology and earth science, one of the hallmarks of what makes it geoscience sort of a complicated field is that you have to understand and confront a large range of scales, length scales and time scales. And that's true for us at the FRP. And what I mean by that is that flow of water in the unsaturated zone and the saturated zone is to a large extent controlled by properties that are at the pore scale, which is microns, like hundredths of a centimeter big. But the Edwards Aquifer region or the system is many miles, hundreds of miles across. So we have to somehow reconcile that discrepancy in scales. And that's definitely something we're dealing with at the FRP. So we have boreholes that go all the way to the water table, so hundreds of feet deep. And we also have boreholes that end within the Vadose zone with 30 feet deep. So we have both kinds of infrastructure for understanding the deep subsurface. We recently had a borehole drilled all the way to the water table, and we actually had the unsaturated part of that well. We used a drilling method that produced cores, so little cylinders of rock that we have saved, and we can use in the lab to characterize the properties, so we can understand the flow properties of an unsaturated zone. Having core samples that deep is a very valuable, very rare sort of set of information that we can get out of that. And then we also have boreholes drilled in a unconsolidated river deposit that are 30 feet deep. We also have samples saved from there, so we can also characterize that material.
Wow. And so I know the Edwards Aquifer, it started forming around is it the Mesozoic era? So,
yes, that's right. I believe that's right. So the Cretaceous.
Yeah, the Cretaceous.
I was just
period,
trying
right?
to visualize the geologic timescale, which is hard for me.
But so when you were doing the core sample, how old is some of that? The lowest stuff in that?
Roughly 100 million years.
That's so cool. So you extracted that from the ground, and you're seeing something that someone has never seen before.
It is extremely cool. It is extremely. People have. I mean, those specific rocks that we pulled out. No one's ever seen.
Yeah.
They are connected to a larger system of rocks that are pretty well studied. But yeah, I agree. It is an amazing sort of experience to see the rocks come out of the ground that haven't been seen in 100 million years.
That's crazy.
Or created and have never been seen really by anything.
It's given us a little snapshot into something that we can't see, which is the point of these geophysics is the same way. It's giving us a snapshot, a look into the subsurface without having to core, without having to drill down.
Yes.
So talk a little bit more about that, Logan. What sort of information is nuclear magnetic resonance and resistivity? What is it giving us? What does it show?
And can you also explain, can you paint a picture of what these tools look like?
Yeah, absolutely. So one thing to talk about is that there are two sort of broad categories of geophysical methods. One is a surface geophysical methods, and others are borehole geophysical methods. NMR tool is a borehole method, and our electrical resistivity system is a surface method. You can have borehole resistivity and you can have surface NMR. We just happen to have the borehole version of NMR and the surface version of resistivity. But it's nice because they give you different kinds of information. So surface geophysical methods are nice because you can take measurements over a relatively large area. So our resistivity system, it looks like the brains of that system is basically a big box with some knobs on it, and
some batteries.
Yeah, hooked up to some batteries or a generator, and connected to the box are 2 long cables with a bunch of little metal takeouts that we connect to metal stakes. So you can imagine a box in a field with 2 long cables extending in a line in either into opposite directions, and that cable is connected via little springs to a bunch of stakes that we drive into the ground.
It's like a probe or like meat thermometer, kind of like if you.
Yeah, the stakes look like a meat thermometer,
like a tent stake even.
Oh,
yeah,
okay.
Just imagine like a metal stake, and it's connected to a wire. So you can determine the spacing of the stakes, and that geometry is important for what kind of information you get.
Oh.
The more widely the stakes are spaced, the deeper you see, but lower resolution.
Oh.
And so, yeah, you have big cable laid out across a field, or in our case, maybe like a wooded zone with lots of poison ivy or poison oak, and probably bees and other other dangerous things.
Snakes.
Yeah.
Yeah.
And so really, it's not very impressive to look at, but what's happening with the electrical resistivity method is because the cables are laid out over a large area, we get information over that whole area. And so by large, I mean, it could be up to off the top of my head, it's maybe like 100 feet roughly if you at max, and you can have smaller or longer surveys. And again, the longer the cable is, the deeper you can get information, but at a lower spatial resolution. So you can imagine, it's an analogy I like to use is maybe taking a photograph. If you use a wider lens, I actually don't know that much about photography, but you can see more maybe in your field of view with a wider lens. But the resolution, if you zoomed into that picture, maybe you wouldn't see as much detail as if you used a zoom lens where you see a less wide field of view, but now you can zoom in very closely and see more pixels per.
So the instrument is passing electrical current through the ground, and certain rocks are more electrical resistive than others.
Like
and
what?
water,
Like which ones?
Logan, why don't you take that
Yeah,
one?
so the way electrical resistivity works, there's different kinds of information you can get from it, but the primary one we're interested in is, what you do is, or what the tool does is it'll pick a pair of stakes, and it will inject current into them, and then another pair of stakes measures the voltage difference at them. So an analogy I like to think, I always like to use, I like water, I like hydrology. So, and the same physics that describes like the flow of water describes electricity. There's a lot of analogies you can connect. In fact, Ohm's law, for those that remember high school, maybe college physics, is the same exact form as Darcy's law, which is what governs flow in water. So earlier I talked about hydraulic conductivity. That's analogous to electrical conductivity when you're thinking about electricity. But so you can imagine like pumping water into the ground and then measuring the pressure of the water somewhere else. And that tells you something about the rocks in between where you're measuring and where you're injecting current. So like Brent said, electrical resistivity is a classic geophysical method in that it measures something that you don't actually care about, which is the resistivity of earth materials. That's the number that you get out of an electrical resistivity system. But what's interesting is that the resistivity of earth materials is controlled by properties we are interested in. Specifically, water content is a big one. That's the amount of water in the ground really dominates the resistivity of the system. Basically, air is very, very resistive. Rocks are fairly resistive. Water's, when it has some salt or electrolytes dissolved in it, is fairly conductive. And so what's tricky about resistivity is that the resistivity of earth materials is not just controlled by water content. There's a lot of factors that determine the resistivity, including the mineralogy of the rocks or soil that you're measuring. Actually, the tortuosity, which I mentioned earlier, does affect resistivity. But a nice thing for us is that only water content or the amount of water in the ground is the only electrical property that changes on the timescales that we're interested in. So if we set up a measurement, every electrical resistivity survey, take a measurement, and then let it rain, take another measurement, the only thing that affects the signal that has changed in between the two measurements is water content. And so when you take a time lapse like that, it's a much easier to interpret the results. So we're lucky at the EAA, or we have the opportunity, because we have our own electrical resistivity system, we have our own field site with lots of access, we can set up these time-lapse electrical resistivity surveys and get a lot of information. We can essentially, with this method, take images of the subsurface, and if we set up the experiment correctly and things don't go wrong, we can essentially get pictures of water infiltrating into the Vadose zone.
Oh, wow.
and leaving the unsaturated zone, and get a pretty detailed understanding of the geometry and spatial and temporal dynamics of how water's flowing in the unsaturated zone.
Right, because the rocks are the same.
Yep.
The rocks haven't changed. The only thing
Yes.
that's changed, the only variable that's changed is how much water has gone into the ground and where it's moving.
Oh, interesting. And so the data that's collected with the tool, what is it like number data that then you all input into like modeling? Okay.
Yes. So with electrical resistivity, in general, all geophysical methods, because what you measure is something that you're not necessarily interested in, you have to do a mathematical procedure called inversion to get out information that you're actually interested in. Our tool, so there's lots, and inversion is not it's not a unique, there's lots of ways to invert the same data. And we have, so there are fortunately schemes that people have come up with, inversion approaches that are well established that we have access to. We get the data from the tool, we process it in an inversion processing software, and we get out pictures from that.
Oh, like actual pictures.
Yes.
Images, yeah.
Oh.
It's like illustrations of the data.
Really?
Yeah, it shows you, where are highly resistive areas versus less resistive areas, and you can make
Yes.
inferences on what type of rocks those may be. Or
So the least resistive it is, the more there's probably water there.
That would be the first in order interpretation. Yeah,
Okay,
absolutely.
okay.
And another, you can also there's resistivity, but we could also say electrical conductivity.
Okay.
And then it's like where the subsurface is more conductive, a good interpretation might be that there's more water there.
Okay.
But we have to be careful because there are other things that affect that interpretation. But if we do time lapse, then we're almost, if we take two measurements and one part of the subsurface all of a sudden becomes much more electrically conductive, it's almost certainly because there's more water there now.
Interesting.
that's what's so cool about it.
That's
Because
cool.
if you do it in the same place across different time, when you have rainstorms and flooding and stuff, that's where you can see changes.
Wow. And so then when you all do these studies and you do like the time lapse kind of comparison thing, is it always because of rainfall, or is there something else happening underground, or is it always rainfall?
That's a great question, and it's sort of a subtle question that people that only think about groundwater might. It's something that in talks, people that study groundwater, I talk about the Vadose zone. People that study groundwater will ask is there lateral flow through the Vadose zone? Essentially, in a groundwater system, water can enter into a little region of the system that you're studying because the water is flowing downhill, essentially. In the unsaturated zone, that can happen under specific circumstances, but in general, it doesn't.
Okay.
Because the water is bound to the solid phase in the unsaturated zone.
Like a sponge.
Like a sponge. In general, it's safe to, as a first order approximation, assume that water is really only traveling vertically under the influence of gravity in the vadose zone. So yeah, if you see an increase in water in the unsaturated zone, depending on the system, you have to take the context of and the geometry of whatever site you're studying into account. It's almost always because water has infiltrated vertically under the influence of gravity from like a rainstorm down. Now, when water leaves, it's a little more tricky because there's two main ways water can leave the unsaturated zone, which is it can percolate downwards past wherever you're studying, or it can be extracted by roots. And it's more difficult to tease apart. If you see water leaving the system without extra information, it's ambiguous how it left. So it's important to measure those fluxes of water so that you can help constrain your water budget in that way. So at the EAA, in principle, we're measuring evapotranspiration. So, if everything goes smoothly, which it never does, we could maybe attribute changes in water content in the vadose zone. We would, in principle, know how much evapotranspiration is happening. We could say that any difference if we have a certain amount of water that has left our study zone, if it's more than can be accounted for by evapotranspiration, we might be able to say, okay, that water percolated downwards.
But then what about you said the borehole NMR?
Yeah, borehole NMR. So first, borehole methods are nice. So electrical or surface geophysical methods give you information over a relatively large lateral extent. But they give you a relatively poor resolution within that lateral extent. So you get a lot of information over a large area, but not a lot of detail within that area. Borehole methods are the opposite. You get basically information at one point on the surface, or like one point in Earth, or it's at different points within a hole, but at a high resolution. So you can imagine if you have a system with a lot of layers of material, for example, that are thin. Let's say like sand and clay layered on top of each other. With electrical resistivity, all of that detail of the layers kind of gets smoothed out into sort of one like average value. And that average value is good for some things, but if you are concerned with maybe how quickly, what you don't get is the fine resolution of the different layers. For example, in this analogy, the borehole method will be able to resolve those fine vertical changes in properties. So that's the beauty of borehole methods, is that you get a high vertical resolution, which you don't get with surface methods. Surface methods give you a large space lateral view, but poor vertical resolution. Borehole methods give you a small lateral extent, but high vertical resolution. So the surface and borehole methods are complementary that way.
Oh, okay.
Because they kind of the weaknesses of one are compensated by the strengths of the other. So that's what's nice about borehole methods and what borehole methods are. So and in general, a borehole method is you have a hole in the ground and you stick a probe or some sort of tool, you lower it into the hole and allow the tool to make measurements in the hole. And that's why it's high resolution, because the tool is very close. The thing that's making the measurements is very close to what you're making measurements of. On the surface, you have to inject current deeply into the earth to get information about it, and that current gets dispersed and the signal to noise gets lower, and so you get a low resolution, but because it's has to travel a long ways. But with a borehole method, you're bringing the tool into the subsurface, and it can make measurements very close by. So our borehole method is a nuclear magnetic resonance system, NMR for short. Electrical resistivity and NMR both developed in exploration for hydrocarbons. So there are those tools. So electric resistivities, like a borehole resistivity tool, is my understanding is a conventional method. Almost any time an oil company drills a well or a borehole, they'll get a resistivity log and a gamma log and a neutron log. Only in very special circumstances will an oil company use NMR, because it's expensive and slow. But what's nice about NMR is that I've heard it described as a luxury measurement in oil and gas.
Interesting.
Because it's expensive, but you get a lot of information from NMR, information that other methods don't give you. What's really nice about NMR specifically for hydrogeology, and especially for unsaturated zone explorations, is that NMR is directly sensitive to water content. So earlier, we talked about with resistivity, it's sensitive to the resistivity of the earth materials, which is influenced by the water content, but also influenced by other things. NMR is, in principle, only sensitive. It's directly sensitive to water content. So it doesn't matter what material, in principle, with caveats. It doesn't. The earth materials don't generate a signal that the NMR captures directly. So if you have a sand with 20% water content, the NMR will measure 20% water content. If you have a limestone with 20% water content, the NMR will measure 20% water content. So that's a huge bonus for Vadose zone studies, because we don't have to account so much for changes in material properties to interpret the signal from NMR, which is nice in the Vadose zone, especially the deep Vadose zone, where we don't necessarily know what all of those changes in material properties are. At the FRP, we have, like we talked about a minute ago, we have samples of material from lots of different parts of the Vadose zone, which is useful for interpreting other methods. But even when you have those samples, it's a lot of work to sort of incorporate all of those changes in the material properties to interpret geophysics measurements. NMR makes it a lot simpler by making that not as important. So that's one big benefit of NMR for our Vadose zone studies. Another thing that's very interesting about NMR is that it is also, the signals is influenced by sort of the geometry of the pore space. And what's the physics of flow of water in the unsaturated zone is also controlled by the geometry of the pore space. And by geometry, I mean really the surface area and like shape of the pores in the porous media. It's very detailed, very
interesting,
very small scale properties of the porous media very strongly control the flow. So an example is like the flow of water through a clay, which has very angular and narrow pore spaces, is much, much different than the flow of water in a sand, which has maybe less angular, more larger pores. And NMR is sensitive to exactly the same properties of the pore space that really controls water in unsaturated zone. That interpretation between that part of the NMR signal and flow in the unsaturated zone is a cutting edge part of the field right now, and it's being worked out. But it's there for us to explore at the EAA.
And so when you do the NMR tool and you put the probe in there, and I know like it's the borehole and then the core is what you all took out, but the borehole, is it like cased, or is it just like, is it just like the ground, or like in there?
That's a great question. In fact, we have a set of shallow, quote unquote, in scare quotes, they're 30 feet deep monitoring holes that we designed and drilled specifically for monitoring with NMR. And the NMR tool has a very specific, well-defined volume of investigation, which is, it makes measurements close to the tool. So it makes a measurement like 3 inches away from the sensitive part of the probe. And so our boreholes have to be a very specific diameter to not, if they're too big, then the probe will just measure the air in the borehole. And if they're too narrow, then the probe doesn't fit in the borehole. So we had a very low tolerance for the geometry of the boreholes, which makes them tricky to get drilled, because drill bits have to be a certain size, etc. It would be nice to leave them uncased, like you're talking about, but you run the risk of the borehole collapsing. So what we did is, for our boreholes, is we cased them with PVC pipe and backfilled the annular space between the PVC and the borehole wall with bentonite grout. A nice thing about NMR, again, is that PVC in the grout does not influence the NMR signal. Other geophysical methods, it would. We would have, if you had one borehole that was cased in PVC and grout, and another that was cased in steel and some other kind of like foam maybe, and you made a measurement with resistivity or another geophysical method, you would have to account for the materials in the boreholes and make a conversion to be able to use both those numbers from those two different holes to make them equivalent. NMR, you could just make a measurement in each hole, and you could interpret them the same way.
Wow.
That's what I like about these two methods, or all geophysical methods really, is that they're complementary. They each have their pros and cons. Like Logan mentioned, resistivity is good for a large area, but not good for high resolution. But when you combine it with NMR, you're getting the high resolution in the small area and then low resolution across a larger area, and you can combine both results to make assumptions about what's going on. So they work together.
When did electrical resistivity
You got it.
and NMR, when did those come online? Like, and then how did you get interested in this? Like, how did you go in this field of study?
Yeah. So resistivity, my understanding, 19th century method, fairly old geophysical method, maybe one of the first. I'm not well caught up on the history of geophysics. That's my understanding. NMR, much more recent. NMR tools really were invented, the methods and stuff. The first ones were sort of deployed in the 1950s, maybe 1960s. And so, and they weren't really, in my understanding is they weren't really in deployment until the 60s. And only recently, last 20 years or so, have NMR methods, have the tools, has the technology been like advanced enough to make tools small enough and affordable enough for groundwater studies? And only even more recently have those groundwater tools been downsized enough to be used in unsaturated zone studies. So that's using NMR in the unsaturated zone is definitely unconventional and cutting edge, like I mentioned earlier. I got into using NMR in the unsaturated zone in my graduate research at the University of Texas in Austin. There is interest for the reasons I mentioned, those benefits of NMR, and that it's directly sensitive to water content and it contains information about the pore geometry. Those relationships are well understood because the tools have been studied in oil and gas for decades. They just haven't been applied to the unsaturated zone. So people recognized the potential of NMR in the unsaturated zone. And I just happened to start my graduate school. I have an undergrad degree in geophysics, and I'm interested in hydrogeology and the Vadose zone. So I had the opportunity, my research group had acquired an NMR system right as I was starting grad school. And so it was sort of was
that exciting?
Yeah. Definitely one of the ways I was sold on the program was that by the end of my graduate school, I'd be like one of the experts of NMR in the Vadose zone, which sounds cooler than it is. The reason there aren't
it does sound really cool.
The reason there aren't experts in that is that it's not very useful because you have to push the field forward, which is hard, but it's fun.
Are you going to be in textbooks then? It's going to be Logan Schmidt.
Probably not anytime soon.
Eventually.
Maybe if I play my cards right.
Well, hey, Logan, thanks for explaining to us all about the unsaturated zone, these geophysical methods, and how it's applying to EAA research. This is probably one of the most detailed podcasts we've had.
Oh, yeah, I learned so much.
And it's been an exciting conversation, and we really appreciate your time and you coming and talking to us.
Well, thank you. I don't get asked about this stuff very often, so it's nice to get off my chest.
You just taught me a lot. I learned a lot today.
That's awesome.
Thanks, Logan.
Thanks, Logan.
Thank you.
As always, we thank you for tuning into this episode of the Recharge Zone podcast. Have questions, ideas for topics, or things you would like to share with us? Well, reach out to us by emailing us at rechargezone@edwardsaquifer.org.